Hello, my YouTube name is Tech-ni-shn. I'm based in New Zealand and I have been technicianing for close to 50 years. A week or so ago I showed a video short of some modules which will be tested and assembled into a HF receiver front end. Since I don't know my audience, I will explain some theory first and then continue on until the block diagram and an outline of the tests that I will perform. The receiver has a noise power. This can be calculated from the formula KTB. K is Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. T is the ambient temperature and B is the bandwidth in hertz. From this, a noise power can be calculated. For our example, I'll be using 3000 hertz, the ambient temperature of 17 degrees Celsius, and from this the noise power can be calculated out as 1.2 times 10 to the minus 17 watts. This isn't really a useful quantity, however it can be converted into dBW but also into dBm. In this case it calculates out to minus 139 dBm. In a perfect receiver then this would be the noise level that a 50 ohm termination would exhibit in the receiver. If one has a 10 dB attenuator in front of the perfect receiver, then it becomes a 10 dB noise figure receiver. In the real world, there are losses in components such as filters, diode mixers, and also the IF preamplifier will show a noise figure which is contributed by the internal noise of the active device. If you add a typical HF receiver front end, such as one that has 2 dB loss and in the filter, 7 dB loss in the mixer, and 5 dB noise in the IF preamplifier, then this calculates out to approximately 14 dB. Using the noise power of minus 139 we looked at earlier, this converts to minus 125 dBm with the addition of the 14 dB noise figure. If you put a signal generator from a calibrated source, then the true RMS power meter on the SSB receiver output should increase by 3 dB over your base noise. This is when the noise power and the signal that is put into the front end is added together, approximately 139, excuse me. If you add 10 dB to the minus 125 dBm input level, a 10 dB signal to noise level should be measured on the output. This is typically 0.4 microvolts for 10 dB signal to noise, and is typical for receivers that have a bandpass filter, diode, double balance mixer, IF preamplifier front end. In receivers, in a perfect receiver, if there is no nonlinearity, there is no distortion happening. But in the real world, there is distortion happening because of nonlinear devices such as active components, switches, mixers, and even tuned circuits. If you have multiple signals, such as two signals, then in the nonlinearities there will be mixing, and the most prominent mixing products are the third order products. If you have two signals that are 10 kilohertz apart, then the third order products will be 10 kilohertz either side of those. If you increase the level even further, then fifth order, seventh order, ninth order, 11th order, and so on will be created. You will see these in a transmitter, but normally they aren't tested in a receiver. If you have two adjustable strong signals and you know the levels, then you can measure the something called the third order intercept point. This is calculated from measurements, and in receivers it is referred to the input. However, in separate modules you can refer it to the input or the output stage. If one increases the level of the products, when one increases the level of the products, the third order products increase in level at 3 times the rate of the carriers. So if one increases the input level by 10 dB, the products increase by 30 dB. At some point, those products theoretically intercept with the primary carriers, and this is the commonly called the third order intercept point. If one has an amplifier of 10 dB gain, then we can calculate the intercept points shown in the data below. In the case of a receiver, then we can calculate the receiver intercept point. Using the MDS we had calculated earlier, then the intercept point can be calculated if we put two input signals in at minus 25 dBm and the products appear on the noise level. Using the formula below, then this can be calculated to be plus 25 dBm in this case. The two-tone dynamic range can also be calculated, and using this formulator below, then in this example the dynamic range can be calculated to be 100 dB. The block diagram shown is a layout of the separate modules in the receiver front end. The antenna signal, or the signal generator, will come in through the low-pass filter on the top left. This is quite useful in addition to the bandpass filter, because often the bandpass filter may not have sufficient rejection higher in frequency. If this assembly is used as in a part of a transmitter, then the transmit amplifiers are typically between the bandpass filter and the low-pass filter. The fourth item along is a notch filter and attenuator. Typically the notch filter has less than half a dB in the bands 40 metre band, which is 7 megs, and the 20 metre band, which is 14 megs, it has a typical loss of less than 0.5 dB. The notch filter is quite useful because the response of the bandpass filter may be insufficient, and it would let the IF frequency, which is 9 megahertz, through with less than ideal rejection. Additionally, the notch filter and attenuator has switchable settings, so if the antenna noise level is high, then additional attenuation can be inserted to reduce the noise level into the receiver. Following the notch filter and attenuator is a RF amplifier. This is switchable because in some cases it is not needed when the antenna noise is high. This goes into a mixer diplexer. I have a number of mixers without diplexers, but since I had this one, it is useful to reject the components from the mixer output. I intend using this with a SI5351 oscillator, and we will see how that performs. Following the mixer is an IF preamplifier. This, together with the RF amplifier, are reversible, so it can be used in a transmit situation. The crystal filter is at 9 megahertz, and in this case it has a nominal loss of about 3.5 dB, and the bandwidth is typically around 3 kilohertz at the -6 dB points. Following the crystal filter is a IF amplifier and relay. When used and receive, it will go into a probably a spectrum analyzer for testing, and then into a receiver such as a ATS 20 plus. If I intend using it as a transmitter, then I can use a TX modulator using a similar mixer to what is in the front end mixer, and that can produce a double sideband signal, which is then filtered into a single sideband signal in the crystal filter. The carrier insertion oscillator could possibly be made using a crystal oscillator, or alternatively a SI5351 based oscillator. A possible microphone amplifier or digital mode input could then feed the transmit modulator. An outline of the tests I will be performing. The first item I will test is the crystal filter. This will be tested for loss, ripple, and matching as return loss. I will also measure the -20 dB points, as if I intend using it as a transmit modulator. These are the frequencies at which I will insert carrier. Also, I will be testing for intermodulation, both in band and out of band. Both are important for out of band, primarily for the receiver performance. However, in band intermodulation is also important for both the receiver and especially the transmitter. The IF preamplifier. I have a one using a 2N5109 with a PCB which is available on eBay, and but however I've modified this so it can be used in both directions. I'll check the gain, the return loss, and also the intermodulation. The mixer, I will perform loss, intermodulation, response, and spurious tests. The RF amplifier uses a more modern device, an SMD device, and this has additional modifications to the original amplifier to make it stable at HF frequencies. The tests will be very similar to the IF preamplifier. The notch filter attenuator, we will look at the attenuator loss, the notch performance, and also the return loss. The bandpass filter, we'll look at the loss and rejection, also the return loss. Typically, filters have good return loss inside the passband, but outside the passband, the return loss is not very good. We'll also look at intermodulation on that if it can be performed. The transmit strip is possibly a crystal oscillator or a SI5351 based unit. Also, we'll look at the modulator performance, the microphone amplifier, and if we develop a transmit amplifier, we will look at the transmit amplifier chain. The SI5351 has harmonics. Being a square wave, it should ideally be only odd order, fundamental, 3rd, 5th, 7th, and 9th. If we load the 5351 heavily, then it starts producing 2nd, 4th, 6th, and so on. So we will investigate that. We'll use it to drive a mimic filter and an attenuator to drive the mixer. If we can, we'll look at phase noise. The back end will be, at first test will be to check the sensitivity and the MDS of the ATS20, and we'll try to make it slightly more sensitive to a 50 ohm setup, as I believe the input impedance is around the 1 kilo ohm. And once everything is complete, I will attempt to do the complete assembly testing.